Question 1. There is a 40% chance that the economy keeps sinking into recession next year and a 60% chance that it will rebound. If the economy rebounds, company ABC will hire 2,000 employees. If the economy keeps sinking, there is an 80% probability that it will cut 1,000 jobs and a 20% chance it will go bankrupt, and a 20% chance to go bankrupt and cut 9,000 jobs. The firm's expected job hires cut is closest to. So we're going to be doing a weighted average of the different outcomes here to get our expected number here. So we've got a 40% chance the economy goes into a recession, 60% chance it will rebound. So rebound, we're going to put 60% times 2,000. And then for our economy keeps sinking, we're going to need to add in another layer here, since if this happens, there are two more outcomes. So we're going to do 40% times 80% times 1,000, or minus 1,000 in this scenario, and then 40% times 20% times minus 9,000. And we're going to add those three outcomes together, and that's going to give us our expected outcome. So the weighted average of these outcomes, we've got 0.6 times 2,000, as we mentioned, which is the 60% chance to add 2,000. And then we've got 0.4 times that 0.8 times minus 1,000, which is cutting 1,000 jobs. And then 0.4 times 0.2 times minus 9,000 gives us 160. So it's positive 160. We're expected to add 160 employees. Answer B. Question 2. A random sample of 50 CFA candidates were found to have an average IQ of 125. The standard deviation among candidates is known, approximately 20. Assuming that IQs follow a normal distribution, carry out a statistical test, 5% significance level, to determine whether the average IQ of CFA candidates is greater than 120. Compute the test statistic and give a conclusion. So what we're going to be doing here is we're going to be computing this test statistic, and then we're going to need to compare that to a critical value number. So our critical value in this instance is going to be a one-sided test at 5% significance. So critical value in that instance is 1.6449. So then from here, we're going to be calculating our test statistic. So in these three instances, we're calculating the t-stat. And then what do we do with that? Do we reject the null, or do we fail to reject the null? So in reality, we can rule B out right off the bat. Since our critical value is going to be 1.65, I'll just round up for easy. If we're greater than that, we're going to reject. If we're less than that, we're going to fail to reject. So in this B instance, we're greater than it, and then we're saying that we're failing to reject, but those would be in conflict with one another due to our critical value. So we can rule out B right away. So we're either going to have this t-stat and reject, or we're going to have this t-stat, which is below the critical value, and fail to reject. So let's bring this in and do that math. I've got the critical value number up here, and then the test statistic formula. So it's going to be our sample stat, which is going to be the average IQ of our 50 CFA candidate sample, which is 125. And then we're going to subtract our hypothesized value, which is this 120 number. And then we're dividing that by our standard error. And standard error is going to be calculated as the standard deviation divided by n, the square root of n, so the square root of our sample size. So we get a standard error of 2.8284. So we'll have 5 in our numerator, and then that 2.8284 in our denominator, which gives us 1.7678, which lines up with answer A. And since it's greater than our t value, or our critical value, we will reject that null. Answer A. Question number 3. Consider a 30-year annuity with a first annual payment of $120,000 starting today, assuming an interest rate of 6% per year compounded annually. The present value of this annuity is closest to. So we've got three numbers here. So we're going to be using our time value of money calculator to calculate this. Let me pull in the numbers we're going to be plugging in first, I guess. So the big key here, where I'm sure a lot of you got tripped up or potentially got tripped up, is this first annual payment is starting today. So the first thing we need to do is we need to go into this part of the calculator and we need to, so from here, you're going to hit second and set, and that's how you change this from ending period to beginning period compounding. So it's normally going to be defaulted at ending period. So for this type of question, though, where the first annual payment starts today, we need to set to the beginning. So once we've set to the beginning, then we can go ahead and just plug in these numbers like normal. So we've got N as 30, interest rate at 6, payment at 120,000, and future value is going to be 0 since it's an annuity. And then we'll compute that present value, and we get minus 1.75 million, which is going to line up right here with answer C. And I think if you would have, let's see. So I think if you would have done ending period, we computed present value, you can see right here we wouldn't have gotten that same answer, and it doesn't align with any of these. So you would have hopefully known you needed to change something with your calculator, but the key here is first payment starts today, so we need to set that calculator to that beginning period mode. Answer C. Question 4. The appropriate test statistic for a test of the equality of variances based on 2 independent random samples is the F-test, T-test, or C chi-squared test. So chi-squared test, we're going to rule that out. This is going to be more so related to the frequency of certain responses or observations happening within the samples. So it's not necessarily related to testing equality of variances between 2 different random samples. It's more so looking at the frequency of a certain observation happening more than once or however many times within one sample. And then a t-test, we can rule that out as well. And that's because a t-test is going to be testing not between 2 different random samples, but it's going to be testing something like a random sample against its full population mean. So what's the mean of this population, or what's the mean of the sample, and then comparing that to maybe it's just our hypothesis, or it's the hypothesis of some other larger data set or the population or something like that. So that is going to leave us with F-test, which is going to be our correct answer. And, not really much else to say other than this is kind of the definition or what the F-test can test for. Answer A. Question 5. Rohan Carter is planning to invest in mutual funds. His sole instruction to his portfolio manager is to generate a minimum return of 5%. The mutual funds in which the portfolio manager can invest are given in the following exhibit. We've got the exhibit in these potential mutual funds. We've got X, Y, Z. We have their mean return of 10, 12, and 9. So they all beat this minimum return of 5%. The portfolio manager will most likely invest in. So since these do all beat the minimum return, essentially what we're going to do is use the safety first ratio, which is basically going to help us measure who is efficiently generating or most efficiently generating excess returns above our minimum rate of return. So it's going to be similar calculation to the Sharpe ratio, where we're going to have in the numerator, we'll have our return minus our minimum return, and then we're going to divide by standard deviation in the denominator. So basically what we're measuring here is our excess returns, and then who can get the most excess return per unit of standard deviation or per unit of volatility or risk, however you want to phrase it. So for X, that's going to be 1.667. Y, it's going to be 1.75, and then Z is going to be 2. So the higher the ratio, the better in this scenario, since it means we're making more excess return with less volatility. And that's kind of what we want if we're for anything over 5%. So we're going to go with answer C, mutual fund Z. Question 6. The standard error of a sample mean is 0.59, the sample size is 30, and the mean is 13.5. If the population follows a normal distribution, standard deviation of the population is closest to. So we're given standard error and sample size. So given these two things, we can solve for the standard deviation. This 13.5 number is not going to be relevant. So this is the formula we can use. It's going to be the standard error formula, which equals standard deviation divided by n to the the square root of n. So we're going to be solving for standard deviation given these two variables. So how that shakes out is we get 30 to the fifth which is going to be equal to 5.4772. So this is essentially x divided by 5.4772. So we need to multiply both sides to finish out this algebra. So multiplying that by 0.59 gets us an x of 3.2315, which is going to round right here to answer C. Question 7. Which of the following test is most appropriately used to assess the linear relationship between the ranks of two variables within their sample when the sample data is not normally distributed? So we've got A, parametric tests. For parametric tests, this is going to require normally distributed data, so that's going to rule out A for us. B, correlation coefficients. For correlation coefficients, the ranking part is kind of what throws us up here. So assess the linear relationship between the ranks of two variables within their sample when the sample data is not normally distributed. Correlation just goes from -1 to +1. So it's not really going to be ranked. It's going to be any continuous number within that range. So I don't think B makes sense for us. Let's make sure C is what we're looking for. Spearman rank correlation tests. Again, that rank kind of gives it away in the question and answer. So we'll go with answer C, Spearman rank correlation tests. Question 8. Bob McAllen, 58 years old, is on the verge of retiring. He owns a savings account amounting to $1.25 million that returns an average of 7% per year. Life expectancy for 58-year-old men is estimated at 25 more years. Considering that he uses this information alone to plan his retirement, the amount that Mr. McAllen can take out of his account every year in living expenses for the rest of his expected life is closest to. All right, so let's pull up our calculator here. We're going to be using time value of money to calculate this. I'll pull in our inputs, I guess, first. So for n, we're going to be putting in 25 for number of years that we're going to live. For interest rate, we're assuming 7% return. Present value is going to be 1.25 million. And then our future value is going to be 0, since we're basically going to be, what we're calculating in this problem is how much money can we take out given these assumptions over 25 years and then end up with $0. And then we'll be solving for payment, which is going to be the amount we can take out yearly. So we'll hit compute payment, and we see we get 107,263, which is going to be closest right here to answer C. Question 9. Portfolio manager compares the performance of a client's portfolio before and after the inclusion of real estate. He has compiled relevant data in a table. He aims to analyze whether the variance of quarterly returns has changed significantly between the two periods. He collects data 5 years before and 5 years after the inclusion. So we've got all that data here. Using a 2.1555 rejection point, so this would be kind of our critical value in this case, the manager will most likely conclude that the inclusion of real estate significantly alters portfolio performance, does not significantly alter portfolio performance, or has an indeterminate effect. So when we're comparing the variance from two different, it's not data sets, but kind of two different runs here. So we've got one simulation without real estate and then one with real estate. When we do that, we're going to be comparing these variance of returns, and we're going to be doing an F-test. So this is what that formula looks like. We're basically just going to be dividing the variance of returns before inclusion and then dividing that by variance of returns after inclusion. And when we do that, we get a number 1.49. And so this is what we're going to be comparing to this rejection point. So if we were above the rejection point, that would allow us to reject the null. And if we're rejecting the null, then we could say that there's statistical significance that it does alter portfolio performance. But since we're below our rejection point, we are going to be not able to reject the null. So we can't say there's an indeterminate effect we're going to say that it does not significantly alter, and by significantly, statistically significantly, alter portfolio performance. And we'll go with answer B. Question 10. A financial risk manager has 3 routes to get to the office. The probability that she gets to the office on time using routes X, Y, and Z are 60%, 65%, and 70%. She does not have a preferred route and is therefore equally likely to choose any of the 3 routes. Given that she arrives to work on time, the probability that she chose route Z is closest to. So this is going to look like a very big and bulky formula here, but let's break this down what it actually is. So our numerator is going to be basically the route that we did choose. So since we're indifferent of each route, we're going to weight the probability that she chose it by 33% or 1/3, and then we're multiplying that by choosing route Z, which is 70%. So that brings our numerator to 0.23333. And basically, this is just kind of the weighted average probability of, or the weighted probability of choosing that outcome. And so then in our denominator, we're going to have all 3 of these different outcomes. So we're going to weight each of these by 1/3 since we are indifferent to each route, and then we're going to multiply them by their respective percentages. So essentially in the denominator, we're getting a weighted average expected arrival of getting to work in general. So whether we take any route, what's the probability that we'll get to work on time? So it's going to be 1/3 times 0.7, 1/3 times 0.65, and then 1/3 times 0.6. And then that's going to lead to our denominator. So when we work that math through, it gives us 0.3589, which is going to round to answer A, 0.36.